making sure that everyone remembers what surface waves were and what we talked about last. If you don't remember, it's not a problem. Just look at your notes, and especially this last slide that we kind of fill this up together when I ask you what is the difference between surface and body waves. In terms of propagation direction and particle motion, does anyone want to tell the class how different surface wave is from shear and compressional wave, just to warm up after the break? Doesn't have to be right 100% either.
The surface waves have both components, normal and parallel to the direction of motion, whereas body waves are either or.
Exactly. So as the waves propagate, compressional wave, the particle motion is perpendicular to the direction. Shear waves is, the compressional wave, they are parallel. Shear waves are perpendicular. It can be like this or like that. And it turns out that surface wave has both. It has a perpendicular component and it also has a parallel. So the motion is like an elliptical motion. And if you remember, it changes on the surface. It's going like that. If you go a little bit deeper, it's kind of retrograde elliptical motion. It is useful for the discussions that we have coming up to remember what these were. I give you 30 seconds to look at these graphs and then ask for a volunteer to remind us all what these graphs are showing us. Because that's a very important property of surface waves, and I want to build upon that to explain some of the applications. I don't know how long is 30 seconds. You count Mississippi, right? On Mississippi. Mississippi. Did I ever give you handouts?
No. It's fine.
Okay. Is there anyone who wants to start with these graphs? Let's look at the one on the left in particular. What does it show? Yes.
That relative displacements shallower are greater, but then there's a moment where as you go deeper, they reach a minimum and then start to increase again for the display on the left.
Exactly. So if I want to sum up this, Tim was very accurately describing how it behaves, but if I want to sum this up, what we see here is the displacement with depth. And we are looking at both components. This is out of plane, like this component, if this is the propagation direction. This one is out of plane and this one is in plane. What we see in a nutshell is that the displacement is limited within, let's say, 1.5 times the wavelengths. Because after that, you see, it becomes very, very small. So surface waves don't travel only on the surface. They actually travel within about a wavelength, 1.5 wavelengths. Into the material. But then they diminish very fast. And what else we see here is that on the surface, the out of plane is larger. Right? So this turns out to be a very, very important property of surface wave that people have used to develop applications. Let's go back here. So this is my version of this kind of graph that we just looked at, and what you see here is that the vertical and horizontal components, they diminish within about 1.5 wavelengths, and also that at some point the horizontal component is changing sign. So that's why I was saying on the surface, you roll like that. If you go 0.2 lambda or so, the motion is retrograde. Another thing that we talked about was, you remember the elephants and so on? We said that the surface waves can travel very far. They attenuate much slower. And that's why elephants can use to communicate with each other in Africa over kilometers. They have found out about that. This is another thing we talked about. This makes surface waves very attractive. And we also talked about velocity, developed some equations, and then we saw that the velocity compared to shear wave and compressional wave is faster or slower? Is the velocity of surface wave slower or faster? It's a little bit slower than shear wave, right? Do you remember the percentage on top of your head? 90%. It's about 90% of the shear wave, but the relationship depends on Poisson's ratio. So this is what we had long time ago, like 2 weeks ago, and we learned about the principles of surface waves. So what I want to do today is go over some of the applications. So surface waves are being used in surface wave testing, as you may imagine. Maybe I bring this here. Kind of like better to stand up. So how does it work? So you have to generate surface waves. One way to do that is to use one of those wedges that you actually designed in your homework that I just returned to you. So you can design a wedge such that the wave, actually what comes out of it, would travel along the surface. I'll take some videos. We have actually a test plan on Friday where we have Teflon wedges and we actually do surface wave testing for a project. If I can send you the info if you are available, you can just stop by to Site, but I'm planning to take some pictures and show it to you next week, just very briefly. But another way that mostly in geophysical and near surface geophysics people use to generate surface wave is simply an impact. So you use a seismic source to generate surface waves. And in surface wave testing for materials characterization, that's what this cartoon that I have here is showing you. So how do we use surface wave testing? Imagine you have a 2-layer system like that. You have one material on the top and one material at the bottom. So consider this. You do this surface wave testing. It turns out that we can get the properties of both layers, including the thickness of the upper layer, from surface wave testing. How? The trick is that, remember, surface waves, they propagate through about one wavelength. We just looked at that. Now, if you look at the velocity versus frequency or wavelengths, what happens in a situation like that, where you have one material on the top and one material at the bottom, is that as long as you are looking at large frequencies or smaller wavelengths, so you're looking at a smaller wavelengths, right? If you're looking at large frequencies or a smaller wavelengths, the whole wave is traveling through the first layer. So the velocity that you would measure would be the velocity of the first layer. Okay? So let's say in the beginning, if the top part is VR1, here is wavelengths. So at small wavelengths, what we are measuring is that the phase velocity is very close to the velocity of the top layer. What happens as we go towards smaller frequencies or larger wavelengths? What happens?
The wave will propagate down into the second material.
Exactly. Then the wave is propagating through both. It's propagating, it becomes larger. So let's use another color. So if we look at, let's say, this point here, the wavelength has become like this. It's a smaller frequency, larger wavelength. So it's propagating through both materials. So the velocity, the phase velocity, becomes a combination of the first layer and the second layer. What happens if you use, if you look at very, very small frequencies? So when you are using a frequency, but this is, of course, it's not white here, it continues. Imagine this continues all the way, right? What happens if you are using a very low frequency, very large wavelengths? The importance of this layer becomes very small compared to this layer. So then it's going to approach to the velocity of the second layer. This is a two-layer system, right? So people typically do that. They try to use a source for surface wave testing, which is broadband. That means that you are exciting a range of frequencies from dark blue all the way to green, so that you can actually have different wavelengths which propagate through different layers in your material. And then you can look at this phase velocity versus wavelengths or frequency, and you see nicely how things are changing with depth. Because the nice thing is, if you plot this versus wavelengths, actually where you see a change, that is kind of where one layer is changing to the other, right? So it is actually quite interesting. But you will soon see that it's not as easy as it sounds so. So people, what they use is that, okay, they assume something for Poisson's ratio, and they turn the Rayleigh wave velocity to, let's say, normally shear wave velocity or P wave velocity, depending on the application. Now, if you have a two-layer system, everything is very easy. Also, if you were only interested in the velocity of the top layer, imagine you have some sort of a structure or a specimen, something that you are just interested in the top 2 inches, in the top 2 meters, depending on the scale. Then you would do surface wave. You just confine your frequencies such that you are looking at the wavelengths which are within that layer, and the velocity would be the velocity of the material. It becomes complicated when you have multiple layers and you don't actually know how many layers and how the velocities are different. Because as you can see here, in this region, the velocity is a combination of the velocities. So then we have to use what is called inversion to go from dispersion curve to a velocity profile. So I'll show you results that, I'll show you many examples of that. But this is the concept. So one thing that I want you to remember is that Rayleigh wave velocity by itself is not dispersive. In a half a space, you saw that it wasn't. It only depends on Poisson's ratio. It has a very ugly equation, but it's not dispersive. But when you go to a multi-layer system like that, it becomes dispersive, right? Because depending on the frequency, you have different wavelengths, and then the velocity changes. This is something interesting to remember. let's see. So this very simple concept has been made into some small size devices. Some of you are geophysicists, you know larger arrays and so on, but there are smaller versions of that. One is this equipment where you have a source, you have a near and far receiver, and then you can get the dispersion curve. And you can just look at if you are interested only if, let's say, in the quality of a slab you are testing, you just look at the velocity at the top, and you don't care, you don't need to do any inversion, etc., and you are good with that. Yeah. This is all. I want to make sure that I say everything I want to say. But in geophysics, most of the time, things are not as simple. So this is now a geophysical data. So let's go back. Let me show you the other one. Maybe we didn't. Okay. So here it's a small device. I forgot. I worked with one for a long time. I mean, the whole thing is this much, like a sewing machine in terms of size. And you just place it. You can move the receivers, and basically you get immediately the dispersion curve. You can plug in the Poisson's ratio, it gives you the modulus, and you are done. You don't need to do any inversion because you are just looking at the top layer. So it's done nice and easy. In geophysics, typically, you need to have, measure the dispersion, and then you actually do inversion. So I don't know if the prints in your handouts are large enough, so let's look at first. So the first step is to get this phase velocity versus wavelengths, the experimental curve. So this is like, haven't written down anything. Let's say if this is a step one, you do develop an experimental dispersion curve. And pay attention that the dispersion, before we were always looking at velocity as a function of frequency. In surface wave testing, it's very common to use wavelengths because wavelengths is very much related to depth. So it's more common this way, and it's the same. So then, what you do is that you come here, you assume a certain layering, certain thicknesses, and certain wave velocities, velocity profile. Right? And then you can calculate the theoretical dispersion curve. You just model it, just like what you did with COMSOL. Now all of you are experts at doing that. And then you do inversion. So you make a model, and then you compare it. So this would be like modeling and inversion. So you assume a certain, you see here, when I say velocity profile means velocity with depth. You assume a certain velocity profile, you feed it into a forward modeling program, whatever you have, you get a theoretical dispersion curve. So you get the theoretical dispersion curve, you compare with the experimental, and then you try to minimize the difference between them to be able to get the velocity profile at the end. And then you interpret it. So there are in geophysics, there are certain characteristics that you know, for example, what type of soil has which range of velocity. So then you and you have some information about the geological characteristics of the site. So you try to relate that and interpret the data.
So in this initial step, wherever, would it maybe be possible to see where there is a significant slope change in the values? And is that where we're determining major harm?
That's a very good question. So the answer is that when you have a very gradual change in velocities, that sharp difference that I was showing you is not very obvious. So typically, the model is based on some information you have from the site. For example, 200 meters away, you know what the site would look like. Or if you don't know anything, you just have to start with a blank model. And the inversion process of surface space is complicated. The optimization, you don't get unique response, etc. But that's a good question and a good point. Is the inversion process clear to everyone? Okay. Now, something that I did not actually talk about very up to now is how would we get this phase velocity versus wavelength or frequency. And the good news is, in the very first homework that I've given you, you actually have once done that. So as I will show you how we would do that, you will remember, I hope. Do you remember this homework problem where there were two spikes, and then you had to, mysteriously, you had to look at the phase, unwrap the phase, subtract the phase, and divide it point by frequency to see that in frequency domain you get the same time shift as in time domain? So now it is the time to see why I would give you something like that. It was very obvious that the spike had moved by one, I forgot the time unit. It was 1 millisecond or something like that. So, okay. How does this work? It's actually quite simple how we get the phase velocity. At least in principle, it's very simple. I need to remind you a few things that we have discussed somewhat long time ago. And this is very easy. One thing that we discussed long time ago was, I think maybe the first class or the second class, was if we had a sinusoidal, here we have time, and here we have amplitude. So this is just a sinusoidal, let's call it, I don't know, sine omega t. How much is this time here? Obviously, the phase of this sinusoidal is not equal to 0. Otherwise, it would start from the origin. How much is this time here? It's not very hard to calculate, right? Exactly. If we say omega t plus phi is equal to 0, so t is phi over omega, right? Here is negative. So now if we had two signals, and one was ahead of the other one, and they had, let's say, let's give them 1 and 2. Let's see, this is 2, this is 1. One way, if I wanted to see how much shift there is between these two signals, I could have compared these times that I'm calculating here, right? I would say, okay, the shift, if they have the same frequency, which they do, would be just the difference between their phase divided by omega. Everyone is okay with that? Okay. that's actually all we need to know. So the time shift between the two signals, we can get it from the shift in their phase divided by omega, which I write as 2 pi f. So, look back at the dispersion curves. What we are looking to get is for each frequency component, what is the time shift between the two signals. Basically, you have imagine you have two receivers, and you want to see at each frequency what would be the time shift between them. Well, it's not too hard. For each frequency, if I know the phase difference, I know the time shift. Now, of course, your signal is going to have a lot of frequencies. What do we do? What should we do? Exactly. We do Fourier transform. We go from time to frequency domain, and at each frequency we do that. And that's how we get the dispersion curve. Very simple. And it turns out that it's even easier than that, because if you remember the convolution of the two signals, if we use something like that in frequency domain, we can immediately get the phase shift between the two signals. So if we have, now I have these receivers, I give this one R1 and R2. Let's actually look at this figure. So that's a very typical, simple surface wave testing. Here you have a source. It could be like something like that. It could be like a wedge, transducer and a wedge. You have, let's say we are just looking at two receivers. We can do this between any pair of receivers. So if I want to have, if I say that R1F is the Fourier transform of basically the signal that you would record at receiver number 1, and R2F would be the Fourier transform of the signal that you would record at location 2. Then all I needed to do was basically get the phase of each one of them, just like you did before, unwrap it, right? Unwrap that and then subtract them and then divide them by frequency. And a better way to do that is just to simplify it and use the cross power spectrum. It does exactly the same thing. I use the same notations that I've used in my notes. So it's defined very simply as, this is more like a practical version of it. This is conjugate, complex conjugate. And these eyes, they are multiple measurements, basically just average. So this is called the cross power spectrum. And the phase of cross power spectrum is actually the difference of the phase between the two FFTs. So instead of doing it manually, you can use this function. But I hope that the procedure is clear to everyone why we do that. Is it clear? Yes.
Can you re-explain what the FFT signal generates a new signal, or going from time to frequency domain, and then I'm not quite following the cross power spectrum.
Oh. Cross power spectrum is just multiplying one FFT by the other one. When you conjugate it, in the exponent becomes negative. So when you look at the phase, then it would be the phase of the first one minus the phase of the second one. So the phase of cross power spectrum is the difference of the phase. It's just an elegant way to calculate this delta phi as a function of frequency. You could have done this manually, meaning that just like what I've given you in the homework, you would get the FFT, calculate the phase of the first one, unwrap it, calculate the phase of the second one, unwrap it, and manually subtract it. But this is much easier to just use the cross power spectrum. It's the same thing, it's just more elegant. This classroom is again very hot. You can see that, like your faces become red and you become sleepy. I don't know why, but okay. I try to keep this interesting. It's quite interesting because it's very easy and the concepts are very easy. So, well, actually, that's pretty much it. Once you have the cross power spectrum, as I said, if you take the phase of the cross power spectrum, it gives you this delta phi. And I hope you still remember how to calculate the phase. How did we calculate the phase before? Remember? So the cross power spectrum is also, it becomes a complex number. It's just like FFT in terms of how it looks like. How would we calculate the phase of this? Long time ago, huh? Think about having the real part on the x-axis and imaginary part on the y-axis and the phase be the angle. Now, how would we calculate the phase? Tangent. Exactly. Excellent. So all we have to do it immediately, if we want to get delta phi, immediately we just use the imaginary part. And right now in MATLAB you just say angle or something like that, and it gives the phase to you. And now you can see where I'm going from here. I have the phase shift as a function of frequency. I know how the time shift is calculated. So the time shift as a function of frequency would be simply the phase divided point by point by 2 pi f, just like in that mysterious homework problem. And of course, when we have the time shift, if you want to calculate the phase velocity, you just take the distance between each pair of transducer, d, and you divide it by the time shift. And you can see that this becomes also, if the time shift is a function of frequency, this also becomes a function of frequency. Also, I hope that you see why we call this quantity phase velocity. If you look at the difference in phase, we calculate the time shift from phase difference. That's why we call this phase velocity. It's very simple. If you plot that versus frequency, you have to start comparing. Right? One last thing. People use, so let me write down that the plot of CR versus F or lambda, which would be CR over F. So it kind of depends on itself, gives you dispersion curve. I think understanding this concept is very important, because this is not only, this can be used for any two signals. If you are interested to see how different frequency components shifting in respect to each other. It's not only for surface-based per se. Let's say if you have a heterogeneous material like rocks, and if you want to see if there is any dispersion, you can use exactly the same procedure to see how different components are different in terms of velocity. Now, one last thing is, often in practice, people want to, field testing, the data is never clean and beautiful, and I'll show you. You see phases which look very noisy, etc. So there is a way people have looked at coherence, which is defined typically as very simple. You get the cross power spectrum. This is R1. We square it, and then you divide it by the so-called auto power spectrum. This is in frequency domain equivalent to cross-correlation coefficient in time domain. So it comes between 1 and 0, how it is defined. So typically, if this value becomes very small, if you want to calculate the dispersion curve between two receivers, your data may not have a good quality. Then you ignore that part of the data. I'll show you why. Question? So these are, this is like if you use the cross power spectrum between receiver 1 and receiver 1. This is like receiver 2 and receiver 2. The same formula. This is called auto power spectrum. You have seen these quantities in other places, right? You have maybe? No, never? Never heard of cross power spectrum? No? Okay. So, but don't worry about it. It is basically, if I put here instead of R2, R1, what I would get would be the auto power spectrum. This is just a way to normalize this. Okay. There are no more formulas, or maybe a little bit, but not much left here. Okay. So now let's quickly review. So the way it works, if you calculate cross power spectrum, because what you're interested in is this phase shift. I hope you are convinced that you can get the time shift from phase shift, then you get the phase velocity, and then you have dispersion curve. Here you can see this process, if you can see. What? Oh, okay, sorry. I skipped one. You can see this process in action. So from the upper left corner, we are looking at the phase of cross power spectrum. So that's the difference in phase. And then this is the unwrapped version that you are familiar with because of that homework problem. So this point A, for example, here, if it is about, 110, if you unwrap it, it comes to about 1,000, something like that. And then you have this unwrapped phase. All you have to do is to use this equation. You have this, so basically this is delta phi as a function of f. Here is frequency, and here is delta t as a function of f unwrapped. So you get delta t immediately from this figure. So you can immediately look at the velocity. I think it comes in the next slide. And what you are looking at here is this coherence function that I was telling you about, and the areas which are kind of grayed out are where you see the coherence falls below a certain threshold. So those areas are being discarded. So you say, okay, this part of data doesn't exist. You try to remove that from your data. This is in practice, that's field data. Okay. Oh, because look here, it's actually a good question. Pay attention to the phase when the coherence is low. The phase doesn't look like nicely as it should. It's basically you have this kind of, and when you look at coherence, it basically picks up those areas automatically. So if you want to see where you have these issues, when you look at the coherence, you kind of can automatically pick those up and remove them. Because you have noise in one receiver, and so then the phase becomes just very noisy. So you were not able to get a good phase between them. Any questions? So when you do that, like this is the continuation of the previous slide. So after you have the delta phi, then you get the phase velocity, and you can plot it versus wavelengths. One thing that I have to note here is that in the field, typically people use different sources with different frequencies, and then they assemble all the data points together to get a large dispersion curve. Yeah. And this is the process of inversion again. So you basically you have the model, and then you have the other model, and then you try to you compare them, and finally you get the final model. I don't know what else to say here. Yeah. This SNSW stands for Spectral Analysis of Surface Waves. Something to know. Any questions? No? Okay. Well, you can see that the process of inversion of surface waves, I mean, I haven't shown you, but it can be a little bit difficult to get both the thicknesses, the velocities, etc. So people have started to develop other methods, which I introduced first by talking a little bit about Lamb waves. So that's the only other place where we have equations. So far, what I showed you with dispersion curve, if you had two receivers and a source, you would be able to get the dispersion curve, and then you do inversion and you get the velocity profile. It turns out that a lot of times you get non-unique answers, and it's kind of hard to do with two receivers and a source with dispersion curve. Typically, you use something which I will show you in a minute. You have multiple receivers, and you use a little bit more advanced way of looking at things. To understand that, it's important to talk a little bit about the waves that actually propagate in place. If you remember, when we were talking about surface wave, how did we arrive at the velocity of surface wave? What was the main boundary condition? Why do we have surface wave? Yes. So this is very related to what Anurup is working on. We had a stress-free boundary condition. On the surface, we have surface waves because we impose boundary condition that there will be no stress on the surface. Otherwise, inside the medium, if you don't have this boundary condition, you would only have body waves. Is this clear to everyone? Or do I have to show you the formulations in the beginning? It's it is right here. So when we were developing the equation, we had to impose this boundary condition that now, if you have a plate, let's just look at one plate. The thickness is D. You have two surfaces, one on the top and one at the bottom. And under normal conditions, there is no stress on the top or at the bottom. So the boundary conditions becomes no stress at this level and no stress at the other level. It turns out that when we do that, we get equations which look like this. Let me write them. I just write the equations without anything more. So if I impose on wave equation stress-free boundary conditions, on the top and bottom, of a plate with thickness D, I get two equations which actually look quite interesting. And let me check. So here I still have to tell you that alpha and beta, what they are. This is really the last equation of today. So, so if you have a plate, the thickness is D, so that's what the D is. Omega is frequency, that's the P wave and S wave velocity, and that's the phase velocity. If you impose these two boundary conditions, you get these two equations. These are actually two equations. One has a plus, the other one has a minus 1 on the top. And the colors they correspond to these two shapes that I have drawn for you. So the plus one is actually corresponds to this so-called symmetric plate waves, right? Or lamp waves. People use different notations for that. So it's called symmetric because it's kind of symmetric with respect to the half plane that goes through. And then the green corresponds to the anti-symmetric mode. It turns out that when you have a plate, very interesting things happen. Let's start from what we understand. If the frequency is very, very high, if you are looking at very high frequencies, the waves do not know that the other surface exists. So it becomes like Rayleigh waves. At very high frequencies, you will have Rayleigh waves, right? Because they don't even know that the other surface exists. That boundary condition doesn't come into play. But when you are in this range, what you have are a combination of different symmetric and antisymmetric modes. It turns out that, let's say, at a given frequency, let's say 2000, here it's normalized, at 2000, you will have different modes. So this is called, like this is one, the fundamental antisymmetric mode, A0. This is the fundamental symmetric mode, S0. And then there is the first antisymmetric mode, A1, S1, and so on. So there are different waves inside the plate, and not every wave, they actually have to fall onto these pairs. And you can get that if you know the thickness, you can actually obtain this dispersion curve for the plate. And towards the end, this goes towards Rayleigh wave velocity, and these go towards shear wave velocity. We won't have the chance to go deeper into this, but this concept is very important. So if you are at frequencies which are here, you are going to, the wave propagation is very different from what you've seen before. You actually have these plate waves that are. And there is not only one mode, you have all these different modes. And this is being used for non-destructive evaluation also, but it's important to understand what this is. I actually uploaded some optional reading on the plate waves from Dr. Rose's book, so you can look at it, because I don't think we will have much more chance to talk about it. Why do I emphasize that? Because I skip one slide. Because there is a way, a very similar concept is being used to improve the SASW, the surface wave testing that I told you, to use a very similar concept. How does it work? So you, instead of just looking at two receivers, you are looking at multiple receivers, or in this case, you move the source. You have one receiver, you just move the source. It's the same, if the source is consistent. So what you are going to get is, at different locations, let's say, you are going to get one record. And what you do typically is simply, you do a two-dimensional FFT. So far, you have done just one FFT. You guys have to go. I only have a little bit more, so it will be in the video. It seems to be working. Sorry. Is it okay? We continue to finish. There is not much. But this is important. The two-dimensional FFT, I think in MATLAB it's like FFT2 or something like that. It's very simple. So you take, instead of one signal, you take one matrix, and then you do the FFT, and you get immediately this dispersion surface, the collection of dispersion curves. So here, this offset between the transducers turns into wave number. And then time becomes frequency. So instead of just looking at the fundamental modes that you would do in surface wave testing, you actually look at the whole dispersion curve. Yeah, I have just written what wave number is, but hopefully you all know. Is this clear what this is about? And it's actually very simple, because if you have multiple records, so you have to have the source at one location, multiple transducers, or you keep one transducer in place and you move your source, at equal intervals, something like that, you get immediately a dispersion curve. So as you can see here, this looks, the modes and etc., it looks just like a plate. If you have a layered system, whether this is in the Earth scale, or is it this is a pavement system, or is it a sandwich composite, you are going to have this kind of dispersion curve. This is much more accurate than just be looking at the fundamental mode and dispersion curve, but the problem is always you need to do inversion. Just looking at dispersion curves by themselves is very hard to understand what's going on. You have to model, you have to compare it to the model to make sense of it. So that's kind of what, I wouldn't say it's a drawback, but that's something that you have to think about these problems. So basically, I hope that this gave you some good understanding about some of the ways that surface wave testing is being used in practice. So I think it's a very good exercise if you try to write down what are some of the advantages or disadvantages of the things you've seen in terms of application. I then decided not to discuss the various structures of the Try to compare the surface wave testing, let's say, to reflection, refraction, the other stuff that you had heard about through transmission, and see what the advantages are and what do you think are the disadvantages. Based on the no, actually the relationship between is the traffic. The group velocity is I actually thought today that I should have had a phase velocity and group velocity. So inside, like, group velocity is the velocity of the envelope. In terms of concept, if you have like different, each one of them may have a different velocity, which is different component, but group velocity is the velocity of the envelope. So, advantages. What are some of the advantages? Let's say if you wanted to sell surface wave testing to someone, how would you start marketing it? Say, this is a good test because, I don't know, this could be your future.
How are they going to do this non-dispersion?
Well, someone would say, oh, well, body waves are not dispersive at all. How do you counter that? What's the counter argument? No, but what would be the advantage from the practical side? You are thinking too scientifically about the advantage. What is one very, let's say when you have your emails, what is very easy about it? Oh, you never used emails. You've seen them.
Yes.
Okay, when you saw that Wang Jung is using emails, what is something very easy, or the things that when Dr. Listener was giving his presentation the other day, what was he saying in the beginning? She was showing how far the transducers are. Exactly. So one big advantage is that you can have your transducers far away from each other. In metals, that I was discussing with Anurup, I'm giving him a hard time because so one project that I was working on with his advisor, so we use transducers which can be placed 2-3 meters apart, and they can still basically inspect the whole area in between them. So we were basically placing them sometimes this far apart, and we could still see what is going on. So that's a real advantage because the attenuation is low. So low attenuation results in large spacing, which can be very practical. In that case, the application is a tank for nuclear waste, and the access to the tank is very limited. So you cannot have two transducers very close to each other to inspect. You have some air slots, and they have to be far away from each other, and you have to inspect the whole tank. So that's one real advantage. Another advantage, very obvious, is when we use true transmission, we need to have access to both sides. Surface network, by definition, everything is on the surface. Source is on the surface, transducers are on the surface. So you just have one-sided access. That's what I mean. I don't know if this term is familiar to all of you. So if you are interested in the near surface properties, if you are interested in just to know what's going on near the surface, it's a very easy thing to do. You just use surface wave and you get the properties. So it's great if you are just interested, great for near surface properties. Now, what do you think the main disadvantage is? What we saw today. Could be an advantage, right? Why? It becomes only the where you would use a very low frequency source, which is actually in practice a very hard thing to do. If you want to go very low, very low frequencies, that you go so deep to use surface wave. That's why people don't use it. Normally surface wave has to you use other methods. You have it. Disadvantage. Well,
becomes fluctuate if there's a vacuum because it has large spectrum compared to the CMS.
so that's good. It's something bad, but that's something we can't do much about, right? That's not the testing. That's just the air creeps when they have the surface. No, this is good. What was the main? Well, the thing is, we haven't done any tests, so you haven't dealt with it. I don't expect that. But think about the inversion process. So if you just have one layer, everything is okay. If you want to have anything like multi-layer, or if you want to do guided wave testing, which is kind of related to that, you always need to model. Without modeling, if you look at the dispersion curve or dispersion surface, it's very hard to see what's going on, right? So I would say the main disadvantage is the inversion, which implies that you need to do modeling always, and that's always expensive, and it takes time. Otherwise, it's great.